Ever needed to maintain a persistent connection to a local MCP server across multiple operations without the overhead of restarting it each time? You'll see how FastMCP's StdioTransport handles this efficiently. The example demonstrates process reuse between async sessions, where the same server subprocess stays alive across multiple connections, eliminating startup latency while maintaining clean session boundaries. This pattern is perfect for local development, where you want both performance and isolation control. From FastMCP client transports, import StdioTransport. Transport equals StdioTransport. Command equals Python. Args equals server, Pi. Client equals client, transport. Async def efficient multiple operations. Async with client. Await client ping. Async with client. Hash reuses the same subprocess. Await client, call tool, process data. File, data, CSV. This demonstrates the persistent subprocess pattern for local RPC communication. The key concept is session-aware process reuse, where a single server process remains active across multiple client sessions to avoid repeated startup overhead. Unlike traditional RPC models that spawn new processes per connection, this approach maintains a persistent subprocess that handles sequential operations through stdin/stdout communication. The pattern works by establishing a long-lived server process during the first client connection, then reusing that same process for subsequent sessions. The transport layer manages all process lifecycle operations, including automatic spawning on first use and cleanup on final session exit. Your tool implementation interacts with this persistent process through standard input-output streams, while the client context manager ensures proper session boundaries. This design balances performance and isolation by maintaining process state between sessions while still providing clean session demarcation. This approach matters for local development and testing, where you need both performance and controlled execution environments. The persistent process model eliminates subprocess startup latency between operations, making it ideal for iterative development workflows. For testing scenarios, FastMCP actually recommends in-memory transport to avoid subprocess overhead entirely, while StdioTransport remains the standard choice for local application integration, where you need actual process boundaries without network complexity. The trade-off is that process reuse means state may persist between sessions, which is why the documentation provides explicit controls for session isolation when needed. Let's break it down line by line. From FastMCP client transports, import StdioTransport. This imports StdioTransport, FastMCP's local development transport that communicates with server processes via stdin and stdout. The example shows process reuse between sessions, where the same subprocess handles multiple async with blocks, reducing overhead while maintaining session isolation through protocol-level separation. Ideal for local development and single-user applications, StdioTransport automatically infers Python file targets and supports both persistent subprocess reuse and per-session spawning configurations. For testing scenarios, the in-memory transport is preferred, while HTTP transport handles production workloads. Transport equals StdioTransport. This configures StdioTransport for local process communication via stdin/stdout, using the specified Python command to launch server, Pi. The transport reuses the same subprocess across multiple sessions as shown in the example, balancing performance with isolation for local development scenarios. FastMCP's transport inference system would automatically select StdioTransport for Pi files, though explicit configuration like this gives you precise control over the command and arguments. For testing scenarios, the in-memory transport is preferred, while HTTP transport is recommended for production deployments. Command equals Python. Specifies the Python interpreter command used to launch server, py as a persistent subprocess. This configuration enables StdioTransport to maintain a single long-running process across multiple async sessions, as shown by the code's reuse pattern, where the same subprocess handles both the ping and tool call operations. The transport communicates via stdin/stdout, making it ideal for local development and testing scenarios where HTTP overhead isn't justified. Args equals server, py. Specifies the Python script that StdioTransport will execute as a persistent subprocess, using stdin/stdout for communication. This transport reuses the same subprocess across multiple sessions as shown in the example, reducing overhead while maintaining session isolation through protocol-level cleanup. The pattern is ideal for local development and testing, where you want process reuse without manual management, with FastMCP automatically inferring StdioTransport for py files and handling the stdin/stdout protocol. This closing parenthesis completes the StdioTransport initialization, configuring it to communicate with the server process via stdin/stdout. The example demonstrates process reuse between async with blocks, maintaining a single persistent subprocess rather than spawning new ones, as shown by the comment, hash reuses the same subprocess. FastMCP's transport inference system would automatically select stdioTransport for Python files, making it ideal for local development and testing, where you want process persistence without HTTP overhead. Client equals client, transport. This initializes a FastMCP client with StdioTransport, which communicates with the server process via stdin/stdout. The transport reuses the same subprocess across multiple async with sessions as shown in the example, maintaining state between operations while avoiding the overhead of process creation. This pattern is ideal for local development and testing, where process reuse improves performance, though for production the HTTP transport would be more appropriate. Async def efficient multiple operations. Defines an async function demonstrating StdioTransport subprocess reuse pattern for local development. The transport maintains a single persistent subprocess across multiple async with sessions, as shown by the code comment, with communication handled via stdin/stdout, ideal for testing and single-user scenarios where process isolation isn't critical. For true isolation between sessions, you'd configure a new subprocess per context, but this example optimizes for performance by reusing the existing process. Async with client. Context manager for FastMCP's StdioTransport. This reuses the same subprocess across multiple async with blocks, maintaining state between sessions while ensuring proper cleanup on exit. Ideal for local development and testing, where you need persistent process state without manual management, using stdin/stdout for communication with the Python server process. Await client ping. This ping verifies server responsiveness before tool operations, using the existing subprocess from the first async with block. The comment shows StdioTransport reuses the same server process between sessions, communicating via stdin/stdout as documented. For testing, in-memory transport is preferred, but stdio works well for local development and single-user applications where you want process reuse. The transport inference system would automatically select stdio for py files, though explicit configuration gives more control. Async with client. Hash reuses the same subprocess. StdioTransport maintains a persistent subprocess for the configured command, reusing it across multiple async with sessions as shown in this example. It communicates via stdin/stdout, making it ideal for local development and testing where you want process reuse without HTTP overhead. For true isolation between sessions, you'd configure a fresh subprocess per session, but this example demonstrates the more efficient reuse pattern. Await client, call tool, process data, file, data, CSV. This executes the process data tool via FastMCP's RPC interface, passing a dictionary payload with the target file. The StdioTransport maintains a single persistent subprocess across multiple async with sessions, as shown by the code comment indicating reuse, with communication handled through stdin/stdout streams. This approach balances performance and isolation for local development, while FastMCP's transport inference system would automatically select this for Python file targets. FastMCP transport reuse. The StdioTransport maintains a single server subprocess across multiple async sessions, demonstrating FastMCP's connection pooling for local Python scripts. Process reuse occurs automatically between sessions while maintaining clean stdin/stdout communication channels, with the server terminating only when all sessions complete. This pattern optimizes local development by balancing isolation with performance, making it ideal for CLI tools and testing scenarios.
The process that never dies between sessions was already dead to the command line.